Okay, in the Jane Austen mini model, in the Jane Austen mini LLM, I made the statement that if I type in Wonder Woman in Midjourney, which is an LLM, it's also a diffusion model, which we'll talk about later. Um, that I get somebody who looks awful lot like Gal Gadot. And that's because Gal Gadot stars in all the Wonder Woman movies. I use the recent ones, like the television show. I don't know what the 70s that is, 90s, something like that. That was Linda Carter. And I'm sure there are, many versions of, other series and things like that of Wonder Woman. I think Wonder Woman actually was in like the 40s. I think she fought Nazis and things in the comics. Not sure exactly, but I think way, way back, like 1940s, fighting Nazis is when the comic started. But I'm not for sure. Um, but if you think about it, think about in words describing Gal Gadot. Just describe Gal Gadot, say, beautiful 30 something, olive skin, brown hair. But a million people are like that or more. Gal Gadot has a unique face. I mean, there might be 10 Gal Gadot impersonators in the world, and maybe your sister looks a lot like her, or family members, or whatever. But if you just use a phrase like, beautiful 30 something, olive skin, brown hair, Wonder Woman outfit, you're not likely to get anything even close. You're just likely to get 8 generic, beautiful woman, 30 something, olive skin, etc. And so, in order for any language model to do whatever it does, it's got to be trained on data. So, there's a Linda Carter picture there. And it kind of doesn't really, really look like Linda Carter, but it kind of looks like Linda Carter's sister. And the prompts I used were things like Wonder Woman, Art Deco Wonder Woman, 1940s comic Wonder Woman, Linda Carter is Wonder Woman, Gal Gadot's Wonder Woman sketch. And even if it's never seen an Art Deco Wonder Woman image, it's seen a lot of Art Deco images. I did a Rolling Stone, and it got the Rolling Stone font well, not perfect, but I'd have to check to see what the font actually looks like. The Rolling Stone label there, but it looked pretty close to me. And that doesn't happen by chance. It happens from your training data. And so even if it's never seen like a Marvel Comics version of Wonder Woman, if it's seen a lot of Marvel comics and the style in which they're drawn, and it has a conception of Wonder Woman by matching image of the word Wonder Woman to images of Wonder Woman, it can create a Marvel Comics Wonder Woman or an Art Deco Wonder Woman or a real life Wonder Woman if there's only comic books and not the movies. And so what these things do is they learn very complex statistical patterns in the large language model, unlike the Jane Austen language model. This is an internet-wide scale. So I can ask it practically anything about anything and at least has some data about it. The more data it has, the closer it's going to be. So if it's a very obscure topic where it doesn't really know much about, then it's going to guess. But if it's trained a lot on Marvel Comics or a particular artist in Marvel Comics style, it's going to win them. It's going to learn what is flat vector art. It's going to associate, if it's training on movies or television shows, it's going to begin to associate that with that term. And then it can put it together in very complex ways. As I said, if you wanted to do, a Picasso Wonder Woman, it's probably trained on a lot of Picasso stuff and it's trained on a lot of Wonder Woman stuff. And then it can begin to associate the patterns. One thing you got to realize is if you give it a lot of things, and particularly conflicting things, like I want something in color and in black and white, it's just going to make a choice. It's just going to decide sort of one or the other. But if you do something like Art Deco Wonder Woman or 1940s Wonder Woman, it'll try to get a feel for 1940s style and, what Wonder Woman looks like and begin to combine them. So both of the small language model, the Jane Austen language model, and the large language model are probabilistic for the stochastic variance. They're both functions that have in and output. But what's different is in the many model, we're restricted to a very, very small set. It has no idea who Wonder Woman is. That's not in Jane Austen's universe. But the large language models are really literally traded on the internet scale data. So pretty much anything on the internet, they have some information about if it's on the internet. And Wonder Woman's on the internet quite a bit. You know, people do up a web page and they put their favorite Wonder Woman fan art or whatever. And, you know, the movies and films and screenshots and all of that stuff. And this allows it to generate very complex, not entirely understandable probabilistic patterns. So it looks like the probability density of a Wonder Woman plus the sort of probability density of what Art Deco looks like. It combines them to make sort of an Art Deco Wonder Woman. So these are very, very complex statistical machines because they're running on massive data sets. So what you got to realize is that, you know, the introducers know every term in the dictionary. And so we're going to talk about this more when we talk about prompting, but the more specific and more sort of information rich you can give the prompts, the better. It understands all jargon. If you're a doctor and you know what hypochondria is, it knows what hypochondria is. It knows every drug name. It knows all of that stuff in terms of mapping terms to ideas. And so the large language models are training on a massive amount of data. They're very, very complex probability distributions, which means they're a little bit more unpredictable because we don't really know where everything is coming from. It doesn't know where everything is coming from. Midjourney tends to make, you know, a lot of women look like supermodels. And it'll sometimes just draw them with barely any clothes on. And it's probably learning that because when it goes on the internet, it's seeing a lot of women with barely any clothes on. Where it doesn't tend to do that is men as much because it doesn't see that data. So whatever data it sees, it's going to learn those patterns. And the different models see different data, which means they're going to have different output. We're going to review all the separate models, Gemini, Claude, you know, all the rest of them. But the main thing here is this is an immensely complex probabilistic machine. There's no chance that I get this thing even remotely looking like Gal Gadot if I'm just using words, you know, beautiful, 30-something, olive skin, black hair, etc. I can do that 100,000 times and never get a picture that looks like Gal Gadot. To get at something even that looks like her, and again, it rarely looks exactly like her because these are probabilistic machines. They just look at patterns and look at probability distributions. But even if it looks kind of like her, if you just put in Wonder Woman and over again it's looking like Gal Gadot, it means Gal Gadot dominates the data that is coming in associated with the term Wonder Woman. Can we see it in the Linda Carter one? Linda Carter doesn't look nearly as much like Linda Carter as the Gal Gadot Wonder Woman looks like Gal Gadot. And the reason for that is it's the data. It's trained on different data. So that's it. I'm gonna go talk about these machines a bit more. I think the next thing I'm gonna do is talk about something called the Chinese room experiment. And that's important also to understand how to interact with these tools. But the summary of these things is these are very complex probabilistic machines. Because they're probabilistic machines, they have stochastic nature. They're random. So even though they're guided, if I type in Wonder Woman, I'll get something like Wonder Woman. I'll rarely get sort of exactly what I'm envisioning in my head one time. And a big part of the process, but they're very, very quick. So a very common thing we do is generate 100, 1,000, 10,000 pictures and pick the best. And we'll talk about how to do that, how to automate that, how to do all of that stuff. This wasn't done that way. I literally just typed in a bunch of prompts. Just, Gal Gadot's Wonder Woman, then Nakura's Wonder Woman, minimalistic poster for Wonder Woman, Marvel comic style Wonder Woman, etc. And just see what I got, because this is supposed to show that what I get is based on the data. If I took in the exact same prompts and asked Gemini to generate the image, or Claude to generate the image, or Chucks, if you did images, they're going to generate different images because they have different data. Okay, that's it. So to summarize, these things know what data they have. You can sort of probe what they data, how they've been trained by what they can do. And I just want you to think about the concept of try to describe a human being in words. And it could be very general. Try to describe LeBron James in words. You can say, athletic, 40, African American, etc. But that's a million people like that. To get LeBron James, you've got to train it on pictures of LeBron James. And then it'll mount the term LeBron James to, what LeBron James looks like. If it's not there, just like with Jane Austen model cannot produce Wonder Woman. If Midjourney wasn't trained on the films, none of its Wonder Womans are going to look like Gal Gadot. 1 out of a billion. So they predominantly do. And that's because of the data that they were trained on. Okay? That's it. We'll go to the next one. Talking about this Chinese room experiment, which again is to help understand these language models for the next video. Thank you.